Hello everyone, you are welcome to part 2 of our lectures in power transmission. Like I told you towards the end of part 1, that some of the problems you will have to solve requires your understanding of the basics of power in AC circuits. So before we proceed, we are going to go through the basic principles underlying the power in AC circuits. You know, sometimes when you talk about a power factor leading or lagging, some have difficulties in understand what it means, and I believe most people accept it in good faith, and they just work with it without really understanding it. So what I'm going to do in this tutorial is to first explain to you what we mean by power factor leading or lagging. Now, the power factor actually comes into play when there's phase difference between the current and the voltage. We have a voltage source, we have a load, and the connection is made from the source to the load, current flows. Usually, sometimes, depending on the type of load, the load may see the voltage first, and after some time starts seeing the current flow through it, or the other way around. Sometimes, depending on the load, once the source is connected to the load, it may allow current to flow through it before eventually voltage is developed across it, and that is what brings about the leading and lagging in the power factor. So first of all, let's look at what we have in this slide. As you can see here, we have the waveform indicating voltage and then current in the resistive circuit, a pure resistive circuit. In a pure resistive circuit, we know that the voltage and the current are in phase, which means that there's no phase difference between them. If you want to talk in terms of time, it means that there's no time difference between them. The time at which the voltage starts is the same time at which current starts. All of them start at the same time. So when you're supplying a resistive load, the load sees voltage and current at the same time. Unlike some other loads that we may be looking at, whether it's inductive or capacitive. So as you can see, the magnitudes may differ, but that's not the focus here. The focus here is the phase difference. So as you can see, this is actually the waveform for current, and this one is the waveform for the voltage. Here, if you are talking in terms of time, you realize that at time 0, they all started. By the time we got to this time, they all crossed the 0 line, and then they all ended up here. They completed a full cycle at the same time. They completed a half cycle at the same time, completed a full cycle at the same time. So they are in phase. Now, when we come to a purely inductive or a pure inductance, a circuit that has pure inductance, you can see that there is a difference in if you talk in terms of time, the time at which each waveform starts is different from the time that each one starts, using the 0 as the reference, the origin as the reference. So here, this is a pure inductive circuit. So what happens now? We are told that usually in an inductive circuit, the voltage leads the current, and if it's a purely inductive circuit, it leads it by 90 degrees. 90 degrees. So we are talking about 90 degrees. We are talking about the phase difference. So what does it mean? First of all, what brings about this lead and lag in the inductive circuit? Now, the inductor is basically a coil, and a very thin one may be called maybe a choke, but basically it's a coil. Now, the behavior of the coil is that the inductor is that it only reacts to changes in current. So long as there's no change in current, it's not going to react to it. So what happens is that once you have a voltage source, and then you also have a coil, an inductor, and there's a switch between. Once you close the switch, what you are doing is that if the supply of the current to that load is let's say 2 amps, once you close the switch, what you are doing is that you are causing a change in current from 0 to about 2 amps across through the inductor. And since the inductor reacts to change in current, and the current is changing from 0 to 2 amps, the inductor is going to react to that change In other words, if it were just a resistor, we are going to say it's going to resist it. It's going to oppose that change. So whilst it is reacting to the change in current, already it is already seeing the voltage. So for an inductive circuit, once you apply the voltage to it, purely inductive, the inductor sees the voltage as applied across it, but then it reacts to the change in current. So the current now is rising from 0 to 2 amps, but it does not get to 2 amps immediately because the coil is reacting to it, on which eventually the voltage is able to succeed in pushing that amount of current through the coil. So there's a time lapse between the time that the load sees the voltage and time that the current starts flowing through it. So if we're talking in terms of the phase, it is 90 degrees. What do I mean? You see this line here. This is the power line. This is the time line. It could also be the phase line. So if you are talking in terms of phases, now let's extend this timeline backwards here. As you can see, this is the voltage waveform, and then this is the current waveform. The current starts from 0 here. Meanwhile, at the time that the current is starting from 0, the voltage is already maximum, as we use maximum. So that tells you that though the current is now starting, the voltage had already started and it's at maximum. So if we can project this thing backwards, it means that the voltage started somewhere here. If you want to bring all of them to the reference point at 0, it means that the voltage may have started from somewhere here. So it covered this distance before the current started. So if, for example, one full cycle is about 360, it means from here to here is 180, and from here to here is 90. So which means that if we extend this to backwards in order to see where the voltage started, it will also be 90 degrees. So 90 here, 90 here, that would have given the half cycle to be 180. Then the full cycle is 360. So which means that the voltage had covered about 90 degrees before the current starts. So that is why we say that in an inductive circuit, the voltage leads the current, or in other words, the current lags the voltage. Now, once you have understood this in terms of the inductor, when it comes to the capacitor, it's always the other way around. While in an inductive circuit, the voltage leads the current by 90 degrees, in a capacitive circuit, the voltage rather lags the current also by 90 degrees. So if you can see it very well, you can bring all of them to one point. Now if you extend this here, you can see this is the voltage waveform, this is a voltage waveform, and this is the current waveform. Now here the current starts at 0 points, from 0 covers 90 degrees here, but then the voltage, if you extend this here, the voltage would have been negative. It means that it has not even gotten to the 0 line yet. So before it gets to the 0 line here, before it gets to the 0 line to even start from that point, by then the current would have covered 90 degrees before the voltage starts. So we can see here that the voltage rather lagging the current in the capacitive circuit. This is very simple. So when we talk about a lagging power factor, we know power factor is a cosine of the angle, phase angle between the voltage and current. That is power factor. So now when we say power factor leading or lagging, usually in power system, when we talk about the power factor lagging, the reference is made to the current. They will not tell you the power factor whilst the current is lagging. Once they say it's a power factor, let's say 0.7 leading or 0.7 lagging, they are making reference to the to the current. So you should take note of that. Okay, so having understood that, if you look at the typical load, like a motor, here we say phase angle between voltage and current in a motor. Now in a motor, we have all these three components: resistance, we have inductance, but we don't have capacitance in the motor. We don't have capacitance in the motor. So here we can say that the motor is an inductive load. But it is not purely inductive because it has resistive components and they also have inductive components. But let's see how the waveform of the waveform in the motor will look like in terms of the power factor. We are talking about the phase angle between the voltage and current. So here, this deep blue line By the way, I am using night mode, so my color may not be exactly the way yours is. 1 minute, let me see the original color so that we can talk at the same level. Okay, good. So now we can see everything clearly. Yeah, so here you can see this is the blue waveform, and then the blue waveform, this is the arrow pointing, it says the total motor current. And then we also have an orange waveform, which is the load current. Is the load current, the current that is actually going to the load, which is doing useful work. And then the black waveform is the voltage applied to the load, the waveform of the voltage. And then the green one, as you can see, is the magnetizing current. So as you can see, there are two types of current in the motor, as you can see it here. We have the magnetizing current and then the load current. The load current, you can say, is the real current which is doing work. The magnetizing current is actually the current that goes into the the coils of the motor, because the motor usually operates by electromagnetic induction, which means that the coils that on the stator windings will have to be energized to produce a magnetic field to interact with the rotor. And then interacting with the rotor windings and the armature windings, as the windings cut through that magnetic field. Well, if it's how do you call it? It causes them. If it's a generator, as the armature windings cut through the magnetic field, power is generated. But in the motor, it's the other way around. You send current into, first of all, you excite the poles, you send current to the armature, and then it also sets its own magnetic field. So the interaction between those two magnetic fields causes the rotor to turn. So here, which means that we need some current to go into the magnetizing circuit of the motor in order for it to work. But the actual current that does the work is the one represented by the orange waveform. So now let's look at the phase difference. If you see carefully, first of all, if you look at the current that is doing the actual work and the voltage applied to the motor, you can see that they are in phase. They all start at the same time. They cover 90 degrees at the same time. They cover 180 at the same time. They cover 270 at the same time, and finish one cycle at the same time. So the current, the load current and the voltage are in phase. So which means that the load current is actually going through resistance. It's resistive. So that's why it is in phase with the current. We know that in resistive circuit, the voltage and current are in phase. But then when you look at the magnetizing current, because those ones go into the coil and you know the behavior of the coil, it means that we expect that the voltage should lead that current which is going through the coil, the magnetizing circuit. So let's see whether truly the voltage is leading this green waveform which represents the magnetizing current. Okay, so let's use the 0 point and the starting point. So you can see the voltage starts here, covers 90 degrees before the magnetizing current starts from the 0 line. So it means that the voltage is actually leading this magnetizing current by 90 degrees, although it is in phase with the load current, the true current. So now we can see we have two major currents, two different currents within the motor. So the two of them come together to give the total motor current. So as you can see, the total motor current is the one represented by the blue waveform. It is represented by the blue waveform. So you can see here that the blue waveform is found between the true current or the load current and then how do you call it, the magnetizing current. So which means that the two of them are components of this. So it's halfway between the two of them. So but then the total motor current still lags the voltage, because because this is not purely resistive, it has a magnetizing current which comes from the coils. So the total motor current also still lags the voltage. So as you can see, the voltage covers about 45 degrees before the total motor current starts from the zero line. So this time, because of the resistive component, you realize that now the voltage is not leading the total motor current by 90 degrees. It is leading it by 45 degrees because of this resistive component. If there were no resistive component and the, how do you call it, the it's purely inductive, it means that we are not even, the total motor current will be just the magnetizing current, and then that one will be at a 90 degrees phase difference from the voltage. So basically this is what happens within the motor. If you want to understand leading and lagging in terms of the power factor, the phase angle between the voltage and the current. So this is what we call the power triangle. Now we have apparent power, we have true power, and then we also have reactive power. Now apparent power is actually usually the power that is sent from the utility, and the true power is the power that is used for useful work by your equipment. And then the reactive power is actually the power which comes as a result of reactive components, like which may come from in maybe an inductor or a capacitor. You understand? So these two now, the true power or the real power and reactive power, they now become components of the apparent power. So if your load does not have any reactive component, it means the apparent power will just be equal to your true power. It means that the power that is sent to you is actually what you actually consumed. So you will not pay extra for reactive power. But if your load is reactive and there are reactive components in it, there will be an additional power drawn by your load as a result of the reactive components, and that will up your bill. So when the utility companies want to bill you, they look at the apparent power sent to you. If you don't have any reactive power, it means that what was sent to you is exactly what you consumed, or what you consumed is what your device could actually get from here without any reactive component drawing extra power. So usually when you want to improve power factor, you try as much as possible to actually, if you eliminate, you're able to eliminate the reactive component, you are fine. Your power factor will be unity. It means that you are not going to have any phase difference at all between voltage and current, and by so doing you will save a lot of money. So as you can see here, the power factor is okay. Let's see from here. This is apparent power, which is the voltage times current, or current squared times the impedance, and then the true power, which is voltage times current times the power factor, cos theta is actually the power factor. So when you pick it from here, and this, which is our true power, and this is our apparent power. So our true power is the apparent power times the power factor. So if you bring these two expressions here, the power factor is the same as true power over the apparent power. That's what we have here. So if you want to make sure that your power factor is 1, it means that what do you do for your power factor to become 1? All you have to do is to make sure that your apparent power and your true power are the same. And that can only happen when there's no reactive component. When there's no reactive component, you are fine. Now, if you change it in a particular way and you swap the power factor and apparent power, and which is the apparent power will now be equal to the true power over power factor. And I'm trying to let you know the essence of improving your power factor. Now, if apparent power now is equal to power, the true power over the power factor. Now, when your power factor is 1, which is unity, it means that it makes your apparent power to be directly equal to the power factor. So if they are charging you, whatever bill you have to pay, it will be the true power that you actually consumed. But once your, once your power factor begins to drop, as the denominator drops, you realize that now we're talking about S equals P over power factor. As power factor drops, X will have to increase. So the more your power factor drops, the more your ampere power increases and the more your bill. So if you want to reduce your bill, make sure that you target your power factor to try as much as possible to reduce it. Okay, so we saw this earlier on. In going forward, we will need this formula to use to solve some questions, but at this level it is not our job to derive them. So when we get there, we'll see what we can do. Same applies to this. Okay, so there are some sample questions here that you can try on your own, and the answers are here. So when you get it correct, you know. When you don't get it, you know that you didn't get it. Then you try again, keep trying until you get your answers. Since this tutorial doesn't have a whiteboard and a marker for me to help you solve, we'll proceed. But make sure that since the answers are here, you know whether you're on the right track or not. And then also, these are the major problems. These are actually the reasons why we had to go through all the AC circuits analysis in terms of power factor, leading and lagging. These are the kind of questions that moved us to actually look at those things. So also with these questions, the answers are here. So when you solve them, you cross-check with the answers to know whether you did the right thing or not. And hopefully, when we don't have to do online teaching again, we'll have the time to go through them. But since right now everything is online, let's keep it like this. Okay, so I think this is going to be our final discussion for part 2, and then we would end everything. So we are talking about transmission line effects. The first one is skin effect, Ferranti effect, coronal effect, and followed by proximity effect and lighting effect. Okay, so let's look at this diagram here. Now, we all know that conductors carry power. When electrons flow through them, current flows through them. That's how they transfer power from one point to the other. But it has been discovered that usually in AC, in DC you don't have a problem. In DC, when electrons are flowing through a conductor, they flow throughout the cross section of the conductor. But they realize that in AC, it is not like that. What happens in AC is that during the flow of current, the electrons tend to flow towards the skin of the conductor, leaving the core almost empty. So assuming you have water to flow through a particular pipeline, and then all of a sudden something blocks the water from flowing through all the cross section here, the internal cross section as has been used, as the dotted lines have been used, and now the same water has to go through the pipeline using only the skin. What is going to happen? The water is going to struggle to flow. So in other words, by restricting the movement of the water to only the skin of the pipeline, what is happening is that you have reduced the area through the outer flow. You have increased the resistance to the flow of the water. So the same thing applies to the current. So long as you have a particular amount of current that is supposed to go through this conductor, but due to skin effect, majority of them are not flowing through the core, but rather on the skin. They are flowing through a reduced cross section of the conductor, and by so doing, the effective resistance, the opposition to that flow will also increase. So by virtue of coronal effect, the resistance of some conductors, especially in AC, tend to increase without necessarily physically changing the cross section. Electrically, the cross section has reduced, and if you look at resistance, which is rho times the length over the cross-sectional area. It means that as the area reduces, resistance increases. So once the area is reduced to only this portion, resistance definitely increases. Okay. Then so these are the factors that affect skin effect: the shape of the conductor and the material, and also the diameter, and then the frequency at which it's operating. These are the factors that actually affect determine the skin effect, the severity of the skin effect. Then we also have Ferranti effect. Now, with Ferranti effect, now we all know that usually it is difficult to find out that if you are sending power from one point to the other, there's a voltage at the voltage at the sending end and the voltage arriving at the receiving end. Usually, it is difficult for you to find out that the voltage at the receiving end is higher than the voltage from the sending end. But from Ferranti's analysis, from which the Ferranti effect came, they discovered that, especially when we are dealing with very long distance transmission lines, you know, the lines act as capacitors. Okay, it acts as capacitance, and then along the path we have packets of impedances, and then usually since the line is considered acts as a capacitor, it means that along the line, if you look at the model of the long transmission line, you can see we have capacitors in the various branches, and they also have the impedances. So if the capacitance, the various packets of capacitors are drawing current, it causes voltage drop across the impedance. If you look at the design, it causes voltage drop across. Do we have that design again? Let me see if we have it here. Okay, so as you can see, so we have the capacitance along the path, and we also have the impedances. So all these capacitors draw current, and as they do, they cause voltage drops across the impedances. So Ferranti is saying that usually what happens is that by the time you put all the voltage drops across the length of the, how do you call it, along the length of the transmission line, by the time you get to the receiving end, it causes the voltage there to be higher than the voltage that was at the sending end. That's what Ferranti said. And we all know that it is not possible for you to be older than your mother. But Ferranti did his own analysis, and since it has been approved, it means that there is some truth in it. Anyway, so that is basically what Ferranti effect is actually about. So he says that due to the voltage drops across the various impedances, by the time you put all of them together and arrive at the receiving end, you realize that the voltage at the receiving end is a little high. And then usually this happens during light load or no load. That's Ferranti effect for you. And then with corona effect, now one major factor that affects corona effect is the level of voltage. When you are dealing with low voltages, corona effect is minimal, or you don't even see it at all. But the moment you are going high voltage, say from 11,000 going, corona effect comes into play. So what is corona effect? Basically, it is a discharge of electrons along the transmission line, and usually it is not every area that you see corona effect. The reason it's not every area is that corona is dependent on the atmosphere surrounding the transmission line. It depends on humidity, because usually corona is actually the discharge of the current through the air surrounding the transmission line. And when the air is dry, very dry, its insulating property also increases. But when there's more moisture in it, it reduces. You know, water is a good conductor, so the more moisture we have in the air, the more the easier it is to conduct. So we know air is an insulator, but air is not. There's no perfect insulator. Every insulator has a breakdown point, and that is determined by the amount of voltage that it is subject to. And then usually the more the voltage, the easier it is to break an insulation, to break or destroy the insulating property of a material. So in high voltages, as current is flowing through the conductor, sometimes when the air surrounding that conductor becomes ionized, once it becomes ionized, it also becomes conductive, and then once a while, or sometimes it can even be prolonged, you see some of the currents charging through the air, and they're continuing in the line and going. So usually this one comes with an arc. It could be in a flash or it could be prolonged, and it comes with a hissing sound and then with some odor. So that is a coronal effect for you. Okay, so I've mentioned the factors. Immediate is one, and the number one is voltage, the voltage level. No matter how humid the atmosphere is, if the voltage is very, very low, you never experience coronal effect. But when the voltage is very high, you are sure to experience coronal effect. And then so we are talking about the dielectric property of the surrounding air as well. Okay, and the proximity effect. Now, when you are talking about proximity effect, one, or should I say two, principles come into play. All those ones have to do with Faraday's law of electromagnetic induction. What is Faraday saying? According to Faraday, okay, we know, first of all, we know that any current conductor produces magnetic field around it, and then the behavior of this magnetic field is dependent on the behavior of the current flowing through it. As the current increases, you expect the magnetic flux, the field, to also widen. As it reduces, you expect it to collapse. Now, when the current is changing or alternating, you expect the magnetic field to also be building, collapsing, and that also be changing. And according to Faraday, when the circuit linking a changing magnetic, when any circuit that links a changing magnetic flux, an EMF is induced in that circuit. When an EMF is induced, which is electromotive force, it means that it can cause current to also flow in that circuit. So which means that if you bring a conductor into a changing magnetic flux, the conductor is likely to carry current so long as there's a closed loop, a return path for the current, which means that the changing magnetic flux will induce EMF into that conductor and cause current to flow through it. So here's the thing. Now, we know AC is alternating current. So when AC is flowing through a conductor, it produces a changing magnetic field or magnetic flux automatically. So if you have a current flowing through a conductor and the current is AC, you are sure that the magnetic flux around is also changing. Now, when you bring another conductor close to it, it means that it will induce EMF in that conductor and cause current to flow through it. Now, the question now is, what if this conductor you are bringing close to this one, the first one, also is carrying current through it? What is going to happen? Each of them is going to induce EMF in the other. And so, if they are in close proximity, whilst this one has producing changing magnetic flux, this one is also producing the changing magnetic flux. So, this will induce EMF in the other, in this one, and this also will induce EMF in the other. So, as a result of this, because of the EMF that is induced, you know that when the EMF is introduced, current is supposed to flow. In this case, we call it eddy current. So, because of this current, which will usually be in opposition to the original current that is flowing, the current that is flowing will try to restrict itself to a particular side of the conductor, which is away from the other conductor. So, in other words, the current will now crowd themselves to a particular one side of the conductor, which is far away, which is not closest to the other conductor. And already we spoke about the skin effect. You see, so once you have the electrons not flowing through the whole cross section of the conductor, what happens? The effective resistance increases. So this is what proximity effect is all about. And usually sometimes they do the arrangement in such a way that along the length of the transmission line, they do some special crossing in order for this effect to cancel out and for it to be minimized. Okay, so say the proximity effect can significantly increase the AC resistance of adjacent conductors when compared to its resistance to a DC current. The effect increases with frequency at high frequencies. Okay, so there's something here for you to read, but basically what I've said explains everything. Once you understand that, you don't have a problem. So you can read this by yourself. Since it is something that anybody can read, I don't want to read it again. What I need to explain from it is what I've explained. So on your own, you can go through it and then make sure you have the full understanding. So that brings us to the end of part 2 of our lectures in power transmission. And I believe in part 3 part 3 starts with power factor. Thank you very much for your time, and I wish you all the best in your exams. God bless you.